Hello everyone, today I will present our work LQ-rPPG, a label-quantized coarse-to-fine framework for robust and efficient remote physiological measurement. In this work, we focus on the quality of PPG labels used for LQ-rPPG training and propose a label-quantized coarse-to-fine learning framework to improve robustness, generalization, and efficiency. Remote photoplethysmography, or RPPG, estimates physiological signals from facial videos. It captures subtle skin color changes caused by cardiac activity. Since RPPG only requires a camera, it enables non-contact physiological monitoring without wearable sensors. From the estimated RPPG signals, we can derive heart rate and heart rate variability. Previous RPPG methods have mainly improved performance through model architecture design. Early learning-based methods used CNNs to extract facial color features. Later methods introduced spatio-temporal modeling to capture temporal dynamics. Recently, transformer and Mamba-based methods have further improved long-range temporal modeling. However, most of these studies mainly focus on stronger feature representations. In RPPG training, contact-based PPG signals are commonly used as ground truth labels. However, these labels are not always clean. They can contain noise amplitude changes and waveform variability caused by motion artifacts or unstable sensor contact. Such inconsistent labels can weaken the stability of supervision. This motivates us to revisit RPPG learning from a label-centric perspective. To address this issue, we consider a more stable form of supervision. Noisy, continuous labels can make RPPG learning unstable, while discretized labels can reduce sensitivity to small label fluctuations. Different quantization levels can provide different supervision granularity. This naturally motivates multi-bit label quantization with coarse-to-fine learning. Based on this idea, our contributions are a label-centric perspective, multi-bit label quantization, coarse-to-fine estimation, strong generalization performance, and high computational efficiency. This slide shows the overall framework of LQ-rPPG. LQ-rPPG consists of two stages: label, quantization, and coarse-to-fine estimation. In stage 1, continuous PPG signals are converted into multi-bit pseudo-labels. In stage 2, the RPPG estimation model learns from these pseudo-labels under hierarchical supervision. The model first learns coarse rhythmic patterns and then progressively refines fine waveform details. The first stage is the label quantization module. Its role is to convert continuous PPG signals into multi-bit quantized pseudo-labels. First, bandpass filtering suppresses non-physiological noise in the PPG signal. Then, a learnable quantization encoder generates bit-level latent representations. Finally, these latent values are matched to codebook entries to generate pseudo-labels with different bit levels. Here, I summarize the main notation used in the label quantization module. The original PPG signal is denoted as Y, and the filtered PPG signal is denoted as Y tilde. The n-bit encoder produces the latent vector Zn. Then, the n-bit codebook Cn is used to quantize each latent value. The final output of this module is the n-bit quantized pseudo-label Yn. The label quantization process can be summarized in 3 steps. First, the filtered PPG signal is encoded into an n-bit latent vector. Second, each latent value is matched to the nearest entry in the n-bit codebook. Third, the matched codebook values form the n-bit pseudo-label. By repeating this process for different bit levels, the module generates multi-bit pseudo-labels. The LQ module is trained to produce physiologically meaningful pseudo-labels. The total loss consists of a reconstruction loss and a feature commitment loss. The reconstruction loss preserves temporal and spectral consistency between the filtered PPG signal and the quantized pseudo-label. The feature commitment loss stabilizes the quantization process by aligning the encoder output with the quantized output. Through this objective, the LQ module reduces label variability while preserving physiological information. The second stage is the coarse-to-fine RPPG estimation model. This model estimates RPPG signals from facial videos using the multi-bit pseudo-labels generated in stage 1. The input video is first converted into temporal features through the frame stem. Then, Mamba blocks progressively refine these features at each bit level. Low-bit supervision guides coarse rhythm learning, while high-bit supervision refines fine waveform details. This slide summarizes the notation used in the C2F model. The input facial video is denoted as X, and the temporal features from the brainstem are denoted as fstem. At each bit level, the model produces restrained features, bit-level logits, and reconstructed bit-level RPPG signals. The reconstructed signals are projected back into the feature space and accumulated for the next refinement step. The coarse-to-fine refinement process is performed at each bit level. First, the previous feature representation is refined by a beat mamba block. Then, the classification head predicts bit-level logits. These logits are converted into an RPPG signal through soft reconstruction. Finally, the reconstructed signal is projected back into the feature space and accumulated. This allows the model to progressively refine the representation from coarse to fine. The C2F model is optimized using classification loss and reconstruction loss. The classification loss guides the prediction of bit-level pseudo-label indices. The reconstruction loss enforces temporal and spectral consistency between the estimated RPPG signals and the corresponding pseudo-labels. Together, these losses enable stable hierarchical learning across multiple bit levels. AUTIS. We evaluated the proposed method on 5 public RPPG datasets: Pure, UBFC, and COHFACE are relatively controlled datasets with limited variations. In contrast, V4V and MMPD include more realistic and challenging conditions. V4V contains spontaneous motion and facial expression changes, while MMPD includes diverse lighting, motion, and skin tone conditions. These datasets allow us to evaluate both controlled performance and robustness under realistic variations. For HR estimation, we used MAE, RMSE, MAPE, and Pearson correlation. For HRV evaluation, we used STD, RMSE, and Pearson correlation for LF, HF, and LF over HF. The framework was implemented in PyTorch, and pre-processing and evaluation were conducted using RPPG Toolbox. Input videos were divided into 160 frame clips, and face crops were resized to 128 by 128. Stage 1 and Stage 2 were trained for 30 and 50 epochs, respectively, and the maximum bit depth was set to 5. In intra-dataset testing, each model is trained and evaluated on the same dataset, LQ-rPPG. Achieves strong results on both controlled and challenging datasets. This indicates that multi-bit pseudo-labels provide stable supervision. As a result, the model can focus more on core physiological rhythms rather than noisy label-specific variations. This slide shows qualitative results of the estimated RPPG signals. Across different datasets, the estimated RPPG signals closely follow the ground truth PPG signals. Even under challenging conditions in V4, V, and MMPD, LQ-rPPG maintains stable periodic patterns. This supports that the proposed framework learns physiologically meaningful rhythms. We also evaluated HRV estimation performance. LQ-rPPG achieves strong performance across LF, HF, and LF/HF metrics. These results show that the proposed method does not only estimate average heart rate accurately, it also preserves physiologically meaningful beat-to-beat variability. In cross-dataset testing, the model is trained on one dataset and tested on another unseen dataset. This setting evaluates generalization under domain shifts. LQ-rPPG demonstrates strong generalization performance across unseen datasets. This is because multi-bit label quantization reduces domain-specific label variations, while coarse-to-fine supervision helps the model learn domain-robust rhythmic patterns. This slide shows ablation studies for the coarse-to-fine supervision strategy. When lower bit supervision is progressively added, the performance consistently improves. The leave one bit out results also show that removing low bit supervision, especially 1-bit supervision, causes clear performance degradation. This indicates that low-bit pseudo-labels are important for learning stable coarse rhythmic patterns. Overall, these ablation results validate the effectiveness of multi-bit hierarchical supervision. This paper proposed LQ-rPPG for robust and efficient RPPG estimation. LQ-rPPG consists of multi-bit label quantization and coarse-to-fine estimation. The proposed framework addresses the issue where noise and variability in PPG labels hinder stable model learning. Extensive experiments demonstrated strong generalization performance and high computational efficiency. Overall, this work highlights the importance of supervision quality in RPPG learning. This concludes my presentation. Thank you for your attention.